Hi, today we're going to be solving problems with similar figures using proportions. And before I show you the PowerPoint, I'd like to show you the accompanying notes that go with it. These are interactive notebook notes that you can use that align with the PowerPoint that we'll go through in just a second. And so you can see the page over here has like guided notes where it's like kind of teacher directed with vocabulary, some background, and just some helpful hints and tips on how to solve. Then there's some guided release examples where the teacher kind of takes students through the problems, and then just some more examples and guided practice. All right, let's get to the PowerPoint. So today we're teaching about similar figures, and this slide is just our intro slide, and it has an example image of indirect measurement, which is one example of how you can use similar figures to find very difficult lengths of things. For example, the height of this tree would be very difficult for this girl to find because it's so much taller than her. Trying to use a ladder would be very difficult because there's all of the leaves at the top. Trying to climb it doesn't make sense. And so she can use the shadows that are created between herself and the tree to find the height of the tree. And that's one of the things that we can do with similar figures and proportions. So what are similar figures? First off, there is a symbol for similar figures, and that little tilde means is similar to. And what are they? They are figures that have corresponding angles which are congruent and corresponding side lengths which form equal ratios. So the two big things about similar figures are their angles and the side lengths. Corresponding angles are congruent and side lengths are form equal ratios. So basically, what does that mean in regular terms? It means they're the same shape figures, but they're different sizes. So how does that work? In this example, we have the similarity statement that says triangle ABC is similar to triangle FGH. So just from this similarity statement, we know lots about these two triangles. For example, we know that because of the order and way that the similarity statement is written, we know angle A and angle F are corresponding angles. So these two are the two angles that are going to be matching in the triangles. Even if I turned them upside down or reflected them or whatever I do to them to move them, I know from the similarity statement that A is always going to correspond to F. Likewise, B and G are sitting in the same position in the similarity statement, so they're corresponding angles. And C and H are corresponding angles. So looking at our definition above, what does it say about corresponding angles? Well, it says that the corresponding angles are congruent. So even though these triangles are different sizes, their angle measures are the same. So angle F is congruent to angle A is congruent to angle F. Angle B is congruent to angle G. And angle C is congruent to angle H. And I have marked those angles according to their congruence. And then the second thing about similar figures is that their side lengths form equal ratios. So the ratio from A to B, or the length from A to B, is the same, compared to the length from F to G, is the same as the ratio of B to C over G to H, which is the same as the ratio of C to A over H to F. And one more side note about similar figures. We talk a lot with similar figures about with polygons. But you should note also that whenever you're looking at circles, not polygons, but still geometric figures, are always similar. So you do need to put that into your brain, the relationship between the ratio and the circumference, and all circles are similar to each other and form equal ratios. Okay, so what if you have polygons where some of your sides are listed and given the lengths of, but some aren't? Well, you can use similar figures to be able to find the lengths of the missing sides. So the proportion that I teach to help my students just know how to be able to find the length of the missing side is that you start with the missing side. So where your variable is, or the side that you're asked to find the length of, put that in the first position of your proportion. Then put it over its length of its corresponding side. So go to the other polygon, find the corresponding side, and put its length down below it. Then go back to the original figure and pick a side from the first figure. And then put it over its corresponding side length. And then you can cross multiply and solve your proportion and easily be able to find the length of the missing side. Another thing you need to know about similar figures, and I referred to it in the first slide, is indirect measurement is the term that we use when we're talking about that technique to find difficult measures. So we can use similar figures and proportions to find distances that are difficult to measure, and we'll see an example of that in a minute. Let's just try to find some missing side lengths and proportions. So we are told that triangle ABC is similar to triangle DEF, and we're asked to find the length from D to F. It's been marked with a variable, so we can start there using our proportion to find the length of missing sides. So we'll start with our variable x. We'll put it over its corresponding side. We know that the length from D to F corresponds to A to C because D is here in this position and F is in this position. And A is in this position corresponding to D, and C is in this position corresponding to F. So we know that it's going to correspond to this 21. And then I go back to my original figure, and I pick a side. I don't know the length from E to F, and so I have to choose 10. And then I put it over its corresponding side. D to E corresponds to A to B. So I put it over 15. Now I have a proportion with a missing side. I can cross multiply. X times 15 is 15x, and 21 times 10 is 210. Divide both sides by 15, and I find the length of my missing side, which is 14. So the length from D to F is 14 centimeters. In our next example, it's triangle ABC is similar to triangle DEF again, but we have two different new triangles. It asks us to find the length from A to C. And so I'm going to start with my missing side length. I know that A to C is the missing side, so I'm going to put X there. Its corresponding side, and I see that this triangle has been turned, and it looks like reflected. And so I need to go here to see which of these three side lengths is my corresponding side to AC. So A to C is here. So I know that it's going to correspond to side DF, which is here. So I put it over 18. Then I go back to my original figure. I only have one option. A to B is not given its side length, and so I only have a 75 to choose. But I need to see which of these two sides is corresponding to BC. BC in the similarity statement is here, so I know it's going to correspond to side length EF, which is 30. Cross multiply, we get 30x equals 1350. Divide both sides by 30, and x equals 45. So the length from A to C is 45. These figures are similar. We have example A and B. Find the ratio of side lengths in simplest form. So I'm just going to set up a ratio of a side length to its corresponding side. So I'll do 4 over 6. And I've got another ratio of 6 over 9. both of those fractions simplify to 2/3, and that's my ratio. And I can write it as a fraction or with a colon or even with the word 2, TO. In my next example B, I only have one side that has the long side of both of the rectangles. So I've got 18 and 24 on my two side lengths, so I can write that. And then I just simplify it and I get 3/4. That's my ratio, and I can write it as a fraction or with a colon or with the word 2 again. So what are some examples of how we could see similar figures in the real world? Again, we talked about indirect measurement, finding things that have difficult lengths to find. A great example is like a cell diagram in a science textbook. Cells are so itty bitty and hard to see. This has been enlarged so that we can see all the parts of it, but the cool thing about these diagrams is that they're proportional to the real live cells. Same thing with a blueprint. A house or a building is very large, but they're scaled down to be something that can fit onto paper so that contractors and construction workers can use those to build it adequately, and they're proportional to the actual building. Just like maps. Maps are proportional to the real world around us. So there are a couple of examples of how you could use similar figures in the real world. Let's try one of these indirect measurement problems. So we have Max here, and he's 6 feet tall, and he's casting a shadow that's 8 feet long. He's standing next to a tree that would be really hard for him to find the height of, but it's casting a shadow that's 24 feet long. How tall is the tree? So he can just measure the shadow of the tree, which is flat on the ground, a lot easier than he can climb to the top of it to find its measure. So let's start by labeling the lengths that we know, and then we can set up our proportion to find our missing side length. So we've got our missing side X over its corresponding height. So we've got height of the tree, it's corresponding to height of Max. Then we go back to the original figure, and we pick the shadow as the only other length that we have, and we put it over the shadow of Max. Cross multiply, divide both sides by 8. We find that X is equal to 18, which means the height of the tree is 18 feet. One more quick example. Here we have trapezoids. It asks us to find the value of X. So again, we're going to find our missing side lengths. And so we're going to start with X, and we're going to put it over its corresponding side. Then we're going to go back to the original figure. When I do that, I do have two options here from which to choose, except when I go to find its corresponding side, I know there's not the short base of the top length here, so I don't want to choose 29. So when I come back to my original figure to choose a side length, I'm going to choose 40, and then its corresponding side is 24, the long bottom base. Cross multiply X times 24 and 9.4 times 40. Divide both sides by 24, and I find my missing side length to be 15.7. All right, thanks for watching. If you would like to find the PowerPoint that is editable, or the corresponding notes that you can take down some guided notes with, all of that is linked below. Have a great day.